Welcome back, students. In this session, we will look at the different types of autoencoders. Already, we have seen the need for autoencoders, which is nothing but a dimensionality reduction process where we try to reduce the dimensions of the data. So now what we are going to do is we are going to find out if there are different possibilities or methods with which you can reduce the dimension of the data. So there are, broadly speaking, there are two types of autoencoders. One is called as undercomplete autoencoders and the other one is called as overcomplete autoencoders. So undercomplete autoencoders are the ones which we have seen so far, in the sense that the number of neurons in the hidden layers will be lesser than the number of neurons in the input layer, which is the default requirement for any autoencoders to have dimensional reduction process. The another type of autoencoder is overcomplete autoencoders. Now you may wonder, how can we get the dimensionality reduced data even though if the number of neurons in the hidden layers are higher than the input layer, which is the case of overcomplete autoencoders. Here you can look at one type of overcomplete autoencoders, which is called as denoising autoencoders, where we try to have a noisy input data and we try to remove the noise from the data by taking only the important features from the data and eliminating the irrelevant features. In this case, we consider them as the noise. So how can we do this denoising autoencoders? So to check or to validate, you can purposely add some noise to the original input data. As you have seen, I have given two input layers, the red color circles in the input part, where the first layer is the original one, and the second layer, the capped one, is the noise added data. So now I have a noise added data. I also have a noise free data. So when I try to match between the output layer and the input layer, or the noisy data and my output, I will be able to get the noisy data. If I get the noisy data, you can see the purple color line where I can subtract it with my original input and generate only the noise. If I can take only the noise, I can easily get the noise-free data also. This is one form of overcomplete. Now, how do we say that it is still an autoencoder? You can closely observe all the neurons in the hidden layer are not used. Some are given a value of 0. Alternatively, in the next iteration, I will make sure some other neurons are given a value of 0. So the ultimate idea is, even though the number of neurons are higher than the input layer, still only few neurons are used. This is the second type of diagram where we say sparse autoencoders, where only few hidden neurons are activated. In the sense, only the neurons with the highest activation values will be triggered and all the other will remain in the off mode. So even though we say it is overcomplete, we can still argue that only few neurons are being taken care of during the implementation process. This is the third type of autoencoders, which we call it as contractive autoencoders, where it is less sensitive to changes in the training data set. As you know, in the deep learning model, whenever a new data is added, you are always forced to change the training process and do everything again and then take the output, which is a time consuming process. Instead of that, if you find only few differences between your original data and the currently available data, do I have a method to get the result without training again from the scratch? The answer is yes. This is nothing but your contractive autoencoders. We do this by adding a regularizer. You have already regularizer methods, L1, L2, dropout, or any different types of regularization functions can be included to make sure that we get the necessary output. So this is all about undercomplete, where you have less number of neurons. It won't be directly copying its input to the output. So don't think we are going to just have same number of neurons and it can be copied. No, because it is passing through the hidden layers where the number of neurons are less. it will be forced to do a generalization process, or it is going to capture only the important features in your data and not all the data, as we saw in the noisy data. If the input data has a pattern, for example, the digit 1 usually contains somewhat a straight line and digit 0 is circular, it will learn that information that this is 1 and this is 0. That is the ultimate objective of your auto encoders. Now here you can see the different types of data, and you can see the original data, you can see the noisy input also, and you can see the auto encoder output. So the objective is same, but instead of having the original data, we are making the challenge a bit more complex and try to find out whether we are able to get the required output even with the help of the noisy input data. And this is the next one, are the widely used autoencoders nowadays, which we call it as variational autoencoders. When you say variational autoencoders, any variations, you look at the first diagram. I am finding a phase and I am saying that in the reconstruction, I am able to find out the exact phase. But how do I do that? For each phase or each image, I am trying to find a discrete point. You can see the picture of Mona Lisa, a small boy, a small girl, and this phase. You can see 4 different points available. Now, if there are any changes, what should I do? I have to go again and do the training process again. But in variational autoencoders, instead of having a discrete point, I try to make a probability curve. You can see in the diagram. So when I have a curve, I have a minimum and the maximum. When the variations are between the minimum and maximum, I can easily adjust and get the output instead of going back again and do the entire process again and again, which will save the time. And at the same time, I can also generate different types of the original input data too, some form of synthesization of the original data. Here you can see the complete architecture where we are not going to depend on the discrete values. Look at the hidden layers where we find a probability curve based on the mean and the variance. Thank you very much, students, for your patience listening. We will come back with another deep learning method in the next session.